Welcome to the presentation of on power transmission line. So in our fourth DGD, we're gonna discuss the different type of power transmission line and how it works. Let's get down. So in power system, the entire system is divided into four parts. It's a generation part, and then it's the transmission part, and then distribution and utilization. That is the consumer end. So transmission line can be subdivided into two types. It's a primary and the secondary transmission line. So based on the transmission line voltage. So typically the transmission line voltage is much higher than the generating voltage. Here we see that the generating station generates typically 11 kilovolt to 13 kilovolt, whereas the transmission line it could be 220 kilovolt or 400 kilovolt. So it depends on the transmission line. So there are some advantages on high voltage in transmission line. So if the voltage is higher, then the line current is lower, and then the transmission line loss I square R would be much lower. So I will show you in the next. So now let's go and the classification of transmission line. Here transmission line is normally categorized into three types. It's a short and then medium and long transmission line. So short transmission line the length can be up to 50 kilometer, whereas the long transmission line is more than 150 kilometer. So now I will show you the ABCD parameters. So representation of transmission line in terms of ABCDs, that is sending in voltage, and the transmission in voltage in terms of ABC parameters. So here we see that the entire transmission line network can be represented in the very simple and equivalent circuit. Here BS is the sending in voltage, where IS is the sending in current, and this is the load side, and this is the transmission line. This is a transmission network. There is a primary transmission and secondary transmission. All is done by a power transformer. So here is the receiving in current, and then this is receiving in voltage. Here load is typically connected. So the transmission line can be represented by just only a two-port network. So if the network is it's a linear representation of transmission line, then according to the Thevenin's theorem in DC circuit, the transmission line expression can be expressed as BS is the sending in voltage, A, B, C, D are transmission line parameters, and BR and IR as the receiving in, I mean the load in voltage and current respectively. So in matrix form, this equation can be written as this way: sending in, receiving, sending in voltage and current. This is the ABCD, and we'll get this equation. So here we see that A and D are dimensionless, so there is no unit, and later on I will show how it's working. And B, the constant B expressed in ohm, and C in Siemens, I mean the mho. Okay, so now it's a short transmission line. The equivalent circuit of the short transmission line can be expressed as this way. This is the sending in, and this is the transmission line impedance. This is Z. This is transmission line impedance, and this is the receiving in voltage. And so the phasor diagram is shown is here. So if here it's a sending in current, and here it's a receiving in current. So in the series circuit, IS must be equal to IR. So it can be represented as simply I. So if I is the reference values, you see there is a inductance is here. So due to inductor, the circuit must be a lagging nature, so the voltage will be leading So here we draw BR is here and I is here. Then what's the equation? How can I write the equation? Just go down. So this is the sending in voltage can be written as BR. Just show the figure. Sending in voltage can be written as in the apply just KVL BR plus IRZ. IR means I, so I and I's are same because the series current remains same. BIR BR plus ZIR. So if I just represent the from here to here, represent the phasor diagram, then if there is I, then the BR is leading because the lagging nature is always defined by the nature of I. So in lagging power factor, I always lags than BR. So here is a BR, and so according to this formula, what we can write is BR plus IR plus R plus JXL. So Z can be expressed this way. So then here is the VR and then IR. So in resistance, the voltage must follow the current because there is no phase difference between voltage and current in resistive circuit. So here's the IR, and whatever the IXL. So if we consider the pure inductor, then it's a 90-degree, the voltage will be 90-degree up. So here's the IXL, and then we'll get BS, just sum of all parameters. So sum of BR, then IR, then IXL, just sum of, this is the BS. So here you see that the current between this is receiving end voltage and this is the current, the phasor I remains the same. So cos theta R is the receiving end power factor, it must be lagging, and whereas the theta is a bigger angle, and the power factor, when the angle is bigger, then power factor is lower. So the angle between sending in voltage and the current is cos theta is sending in power factor. So theta R less than theta S, so power factor cos theta R is greater than cos theta S. Okay, so now we see that this is the Z is a small z, represent the series impedance per unit length. So the total impedance would be just multiplying the transmission line length. L represent the transmission line length, Y represent the shunt admittance. So it's a capacitor in parallel. So you see that the when the for the short transmission line, the length is much lower, is less than 50 kilometers. So the capacitance effect, we can ignore it, the capacitance effect. So shunt admittance is not considered for the short transmission line. Okay, so now the sending in voltage according to KVL, it can be written this, and the sending in current and the receiving in current is same for the series circuit. So if we represent in the matrix form, then we can be written as this way. So now just compare this, this is A, B, C, D, just go up, yeah, A, B, C, D. So here for the short transmission line, A and D is 1. As we said, A and D are dimensionless because there is no unit. B can be expressed as ohm and C in Siemens. So here B represent as Z, so Z definitely in impedance is ohm, and here for the short transmission line, C is 0. So there is no unit here, but we will see in the later for the medium transmission line, C should be inverse sign of resistance, I mean the impedance. So yeah, then we'll get the Siemens. So so there is an expression. So AD minus BC can be written as 1 because A and D is 1 and B multiply C, I mean the Z multiply C equals to 0. So it can be written as 1. So let's see, another phasor diagram can be expressed here. So the same circuit, this is the same circuit, we can draw the phasor diagram in another way. Let's see how can we do. So if here is the reference, let's see, here is the reference, and then the series current, this is I or IR, this must be lagging, this is theta R. So this is here. So what would be the IR? So yeah, it must be IR is follow the current, and this is the IXL and the sum. This is the BS, if BS is the reference. So we can draw similarly the same phasor diagram when receiving in voltage as a reference. Let's see, go down. Here you see that you see here is the reference and the current is lagging, and then what is the equation? This BS equals BR plus I Z, or Z equal to R J XL. Then this is BR, and this is the current lagging I, and so for resistive, so for the resistive part it follow IR, and then IXL just go above 90 degrees. So for the pure inductor, and you just add this point, we'll get BS. So this is for lagging. And what about the for leading? So here's the when the unity power factor, the voltage and current remains the same phase, and IR should be follow the same because there is no phase difference, and then IXL just go above 90 degree, and just sum all the terms, we get sending in voltage. And the for the leading power factor, I must be leading, but yeah, for the for the short transmission line, this would never be a leading power factor because there is no capacitance is here, because we know leading power factor only happens for the capacitive network. So this is the VR. Okay, however, let's see, this is the VR, and the current is leading, and the resistance is follow the I, this go up and then 90 degree, and just sum, will get PS. So approximately the sending in voltage for the if we elaborate this, if we expand this equation, then we'll get this equation if for the approximate expression of sending in voltage in the short transmission line. And this is the voltage regulation term. Voltage regulation can be defined as typically we know it's a B no load minus B full load over B full load into 100. So B no load here is mean as a sending in voltage, and B full load at the receiving end at the load side, it receiving in voltage divided by this, and this voltage regulation BS minus BR represent the voltage drop through the transmission line, because we know BS equals BR IZ, then BS minus BR equals IZ. So it's represent the voltage drop, so it's the voltage drop. So we can write if BS minus BR, then this term is BS minus BR can be written here. So it's for lagging power factor. And what about the transmission efficiency? So efficiency is always output divided input. So here output in the receiving end, I mean the load end side, and this is the sending end, it's in the generation side. So for the single phase receiving in BR cos theta, and so for three phase just multiply with 3 if this is the phase voltage, and this is the sending in voltage, I mean total input power. Here is the input, so it can be expressed in another way. So is the receiving in power divided by receiving in power plus transmission loss. So if there is a three phase, then just multiply 3 over here. So it's the expression of transmission efficiency and the sending in power factor. So go above sending in power factor. So this is the sending in voltage and this is the current, and the angle between is theta s. So there the triangle OCD. So triangle OCD, we can write cos theta is equals OD divided OC. So you see OC can be written as BS and OD can be written as OE plus ED, because OD equals OE plus ED, and if we go here, so ED equals AB equals IR, and what is the OE? So the triangle OAE, cos theta R equals OE divided OA. So we can easily find the value of OE here, because OA is just VR. OA equals VR. Then so if we from the this figure we can write this expression. So it's for sending in power factor, and this cos theta is the receiving in power factor. Okay, now let's see the effect of load power factor on voltage regulation and transmission efficiency. So when the load power factor is lagging, the term IR cos theta R must be higher than IXL sin theta R, because for the lagging power factor the voltage regulation must be positive, because BS minus BR, BS must be greater than BR, because there is a voltage drop along the transmission line. So the term obviously is greater than sending in voltage. Yeah, so for the lagging power for the lagging power factor, the transmission line drop is higher, and so whatever the efficiency, let's see, for a single phase line we can write P equal BI cos theta, and for three phase is 3 BI cos theta. So here star means that this is it's not a conjugate sign, it's just as a notation. This is all on the line to phase voltage. So it's for three phase line and single phase line. So I can be expressed as P divided by this. So when the power factor is lower, so if it is lower, then the current would be higher, the load current would be higher, and the line loss, so line loss, this is the I square R. So it's a square time, so it must be higher, so if the power factor is lower. So on the other hand, if the transmission line voltage, this is if VR is higher, then I should be lower, and then I square R should be much lower. So this is the advantage of high transmission line voltage. So and this is the disadvantage of low power factor. If the power factor is lower, receiving end power factor is lower, then the transmission line loss will be worse. So there is a there should be optimum condition is here. We see so the transmission line voltage would be need to be higher. So let's see some example here. So for a single phase, this is the single phase overhead transmission line. So this is the power at the receiving end, and this is the power voltage at the receiving end size 33 kilovolt, and the power factor is 0.8 lagging. R is resistance, R is given here, and XL is 15 ohm. Then we have to find the sending in voltage. So sending in voltage, here is the sending in voltage. So here, so all of the line parameter are used here. I, so how can I get this I? Because we know P equals root 3 VRI cos theta. So root 3 for this is the line voltage. If we use the phase voltage, then we have to make this is the line voltage is given here. So we shall put, if this is the phase, this is the line voltage, 3 VI cos theta. So from that I will get I value, I should be 41.67 ampere. So whatever the value, because BP should be can be written as BR root 3, whatever the expression, we'll just get the same answer. And cos theta, value of cos theta is 0.6, and sin theta R can be find as a root over 1 minus 0.8 square, and we'll get this 0.6. So this is the sending in voltage expression, and the second part is sending in power factor. So according to the formula, all the value are given here, and the transmission line transmission efficiency. So efficiency can be expressed as receiving in power by sending in power, or receiving in power plus total loss. So receiving in power is given here, PR is here, and so we have to find the loss. So loss for the single phase transmission line, the loss is I square R. So I value, I is here and R is here. Then we just sum the value and we'll get, this is the transmission line efficiency. Let's see another example. So it's a three-phase 50 Hz 16 kilometers. So obviously it's a short transmission line, and the receiving in power voltage and power factor is given here. The line resistance per phase per kilometer, so it's per kilometer, and the line inductance is 0.7 millihenry. And we have to calculate the sending in voltage as well as voltage regulation and efficiency. So what is the transmission, what is the resistance of the transmission line voltage? So for each conductor, you see there is a three-phase, so they found for the per phase resistance, total per phase resistance, so 0.03 ohm per kilometer, and the length is 16, so we'll get the 0.48 for each phase. And likewise the reactance XL can be defined as 2 pi FL, and this is the transmission line length, and the phase voltage. So all the expression are found here using a phase voltage. So it's 11 kilovolt, and then we'll get the phase voltage. And what is the line current? P equals 3 VI cos theta, because all are the phase value. If we use the line voltage, then we have to use root 3 here, and this is the sending in expression because all the value we have in our hand. And voltage regulation, Vs minus VR. Yeah, so the regulation is very low, and the transmission line, so here is the line losses. So the receiving in power is given 1000 kilowatt is here, and the line losses, because the three phase, so we have to multiply over 3 here, 3 I square R, and this is the transmission efficiency. Now let's go in medium transmission line. This is the second type of transmission line. So the transmission line voltage is higher than the short transmission line, and the effect of shunt admittance, the capacitance cannot be neglected, and the capacitance so is uniformly distributed over the transmission line. So here the whole capacitance is divided into two, so it's actually a pie shape. This is the pie, this is the pie shape actually. So here is the capacitance shunt in shunt, and this is the series admittance. So here is the sending in voltage, and this is the receiving in voltage, and this is the sending in current, and this is the series current flow through this series impedance, and this current through this arm is here. So capacitance actually used for the compensation technique. So when the transmission line is getting long, so the the more voltage drop is happening through the series resistance. In order to compensate this resistance, this drop over here, we have to use capacitance so at the both end. So now let's see the expression here. So I see to the current over this arm. So in this voltage can be, but this is the open end size, the voltage is here VR, and then this is the admittance. So I equals B by Z, or I equals B into Y equals 1 over Z. So yeah, so here's the IC2, and then series current through the series impedance can be expressed as, so this is the series, and one current is goes here and another current is divided here, so it can be expressed as this is the receiving end because the load is connected here. And what about the sending in voltage? Sending in voltage according to KVL, so it's I series, this is the voltage drop over here and the receiving in voltage, and we'll get this expression. And what about the source current? This is the sending in current. Sending in current will be the this and this current. This is the parallelly divided IC1 and I series, and I series can be expressed as this, and we'll get this one. So if we just think this is A, this is the generic transmission line, BS equal to AVR plus BIR, whereas sending in current, this is the sending in current equal CVR plus DIR. So here is the value of A, B, C, D. And if we see the unit Z and Y, they can be cancel each other, so it's a dimensionless. Here it's also dimensionless, so it's in ohm, and if these two term cancel each other, so it's dimensionless, but it remains, so its unit is Siemens or ohm inverse 1, as we say in the beginning of this lecture. So yeah, we got the expression for medium transmission line. Let's go for the long transmission line. So for the long transmission line, this might be same as medium transmission line, but this is a modified one, because for the long transmission line there is a incident wave and there is a reflected wave comes into the scenario. So it can be expressed as just like a pie shape, but here is the modified series impedance, and shunt admittance is a modified one, it's a prime sign, so all the parameter remains same, and the voltage and current relationship can be expressed as cosine. It's a hyperbolic function. Hyperbolic is comes because the it's just incident and the reflected wave, and similarly all the expression are same. Vs equal the matrix expression AVR plus BIR and IS equal to CBR and DIR, all the equation remains same, and ZC represent the characteristic impedance and sometimes surge impedance we later on will show, and gamma is the propagation constant and with the power propagation through the transmission line. So here the similarly same A and D can be expressed as this way. B can be this is the dimensionless, B in ohm, C in Siemens. So let's see the example. So all the expression remains same, and we'll get A equals the same expression like medium transmission line, just there is a modified one. So what does the modified one means? Z prime is the ZC is the characteristics impedance. Characteristics define the nature of the transmission line, either is lossless or how much it's lossy line. So it can be expressed as ZC sine hyperbolic gamma, and gamma is the propagation constant. Here is C ZC, small z is the reactance, sorry, impedance per phase in transmission line. ZC is called characteristics impedance, where gamma is called propagation constant. Both are the complex quantity, and the gamma can be expressed as alpha and J beta. So here alpha is called the attenuation, so yeah, you can call this a resistive part, and this is the beta is 2 pi by lambda, it's a phase constant, it's an imaginary part. So in general, so all the ABCD parameter for short, medium and long transmission line can be presented is here. So the expression remains same for the all transmission lines. So now we'll show the surge impedance loading. So surge impedance loading is defined as the power delivered by lossless lines. So when the R equals to 0 to a load resistance, so it's the lossless line, I mean the series impedance. So here R is 0 and load resistance in the receiving end side equal to the surge impedance. So it can be expressed as surge impedance or characteristic impedance is root over L over C. So surge impedance can be defined as in equation, it's line to line voltage square B square divided by Z. Surge impedance, this is the value of surge impedance. So actually the in order to calculate the surge impedance loading is not directly related to the transmission line length, because it's not measure the power transfer capability. So the value of surge impedance loading can be realized is this way, that is it acts as like a shunt reactor when it's absorbing megavar, I mean the reactive power from the system, and is loaded. So when the shunt capacitor, you see in earlier we show that the shunt capacitance, I mean when the capacitor is connected parallel to the load, then the power factor is getting improved and the higher power is received at the receiving end. So yeah, so for the inductive nature, it means that it absorbs the reactive power. So megavar is for a high transmission line voltage. It can be expressed as kilovar or megavar, or no matter what. So megavar for the inductive nature, and this is the shunt reactor, and so it's act as a shunt capacitor when it's supplied to the system and improves the power factor and the receiving power as well. So for the shunt capacitance, the megavar supplied to the system can be expressed as kV square divided by XC, and for absorbing the reactive for the inductance part, it can be expressed as I squared XL, and for the surge impedance loading, it operated unity power factor, because we see there is a lossless line. So R equals, so yeah, lossless line means there is no impedance is there. So it's for unity power factor, because in resistive circuit there is only only in resistive circuit the power factor is always 1 because there is no phase difference between voltage and current, and they remains in the same phase. So theta is 0 in the resistive load. So the surge impedance loading can be expressed as, so for the unity power factor is the maximum power actually. So I square XL, here is the I square XL, these two term equal, ampere just cancel out. So if we put the expression I square XL equals kV square divided XC, and then we'll get this equation, the surge impedance ZC equals Pi equals root of power L by C. Here is the surge impedance when the line is lossless, the surge impedance. So surge impedance means the total power, actually maximum power transfer in the transmission line. So here is the surge impedance root of power L by C, and yes, there's the some similar expression is derived here. So thank you, this is all about the transmission line, and then like in our lecture 2 we'll cover some mathematical problems. Okay, thank you, have a good day.